Okay, so my slides kind of jump around the presentation, so we're just gonna go to procedures first. So to figure out some of the mechanical properties of these polymers, we did tensile testing to generate stress strain curves. So tensile testing is done by cutting out dog bones according to an ASTM standard of the samples, loading them into an Instron universal testing machine set to perform tensile testing, and then running the actual test. So make sure before you do that, you measure the thickness, width, and gauge length of the sample so you can generate your engineering stress and strain afterwards. So just remember, when you're actually doing a tensile test, you generate load displacement charts, not stress strain, so you do have to convert them afterwards, which you need those measurements for. So a typical strain rate is 10 millimeters a minute, but as I'll talk about a little bit later, that can be adjusted up to 50 millimeters a minute, and we actually do that. So afterwards, collect the data in Excel, analyze it, and like I said, change your displacement, change your load displacement curves to stress strain curves. So Archimedes density essentially looks at how the displacement of a polymer in a liquid correlates to its volume, right? So you start by recording the dry weight of the unknown polymer. You submerge it in this case mineral oil. You can do it with water, any kind of liquid, as long as you know the specific gravity of that liquid. And then place the samples into a vacuum desiccator and pump until the bubbling subsides. Also do the same thing with a second beaker of the same liquid, because your next step is going to be placing that second beaker of liquid under a balance and measuring the suspended weight of the samples. Then after you remove it from the submerged platform, dry the surface and record the saturated weight. So during the results, I'll talk about how this can give you really, really good results, but the setup that we have isn't really good for accurate results. I'll again talk about that a little bit later. So moving on to the results that I'm discussing. Okay, so this is the first stress strain curve that we generated for the unknown polymer delta. So I just want to remind you what a stress strain curve for a polymer is supposed to look like and what the material is actually doing during this time. So you'll see this very first leg right at the beginning where you'll look at the elastic modulus, and that is the breaking of the secondary bonds, right? So remember that polymers are just these long chains that are all tangled up together, and as the polymers are just near each other, you're going to get these little van der Waals forces in between polymer chains, right? They're not actually part of the chain, they're just chains near each other, right? So this first part is breaking all of those, right? And then this part here is the polymer chains lining up, and they're going to kind of detangle each other as you're stretching them apart up until the very end right here where it goes up again, and that's where you're breaking all those primary bonds, right? So remember that polymers are primarily CC bonds, and this very end of it is where you're actually breaking those primary bonds. So this is what a typical stress strain curve should look like for a polymer. So the experimental results are on the side. Just remember that this one we did the crosshead speed of 10 millimeters a minute, which is pretty standard. We got an ultimate tensile strength of 43 megapascals, an elastic modulus of 0.54 gigapascals, and then a percent elongation of break of about 888%. So I just want to remind you that even with metals, looking at an elastic modulus from a stress strain curve isn't the best idea. So I really don't want you to focus on the elastic modulus. Definitely just focus on the ultimate tensile strength. So as we were looking at tensile testing for polymers, we found out that the ASTM standard actually says the whole test needs to be done in under 5 minutes. So we definitely didn't get that with the first couple of polymers. It goes to like a half hour, right? So we decided to ramp up the crosshead speed so that you're actually within the ASTM standard of 5-ish minutes. And then to do that, we had to ramp up the crosshead speed all the way to the maximum, 50 millimeters a minute. And I think it still took close to 10 minutes. Which is just under the ASTM standard. So, like I said, the beginning part is the secondary bonds, all the way up to the final, which is you're breaking the primary bonds. We found an ultimate tensile strength of 39 MPa. We found an elastic modulus of 0.461 gigapascals, and we found a percent elongation of 910%. So most of those are actually in line with the first test that we did, which is pretty comforting. So we didn't mess anything up. We just ramped up the crosshead speed. So these are the results we got for Archimedes density. We found a bulk density average of about 1.05 grams per centimeters cubed, but if you look at the standard deviation, it's about 25% of the value that we got. So we really do not want to argue that density should be a result that will argue one way or another for the identification of the polymer. So essentially this is saying that the density of the polymer is between 0.75 and 1.25 grams per centimeters cubed, which is essentially all the polymers that we are choosing from. So let's not look at that, let's move on. Okay, so this is the stress strain curve for the unknown polymer gamma. The ultimate tensile strength looks to be about 83 megapascals, the elastic modulus is 0.811, and the percent elongation of rate was 325%. We did the exact same thing where we ramped it up to a higher strain rate, and we got something that looked like this. Ultimate tensile strength ended up being 73 megapascals, elastic modulus was 0.811, and then the percent elongation was 260. So pretty close to the first one that we did, but in the ASTM standard time window. So this is the Archimedes density data for the unknown gamma. This one had an average density of 0.74, and then again a very high standard deviation of 0.16. So that ends up being pretty close to like 20% of the average value. So you're going to get something that's way too wide of a window to call good results. So in conclusion, we decided that the delta was polypropylene. We really wanted to get something more specific than polypropylene, but we really didn't have enough evidence to pin down exactly what it was. So if you look at the results that we talked about throughout the whole presentation, they're kind of summarized here on the slide. You'll see that the melting temperature was very spot on. We got a value of 164 about, and all the literature values we found were 160 to 165, so we're really happy about that. The ultimate tensile, again, was really, really spot on. We found values to be 39 to 43 MPa, and the window is coming from the two stress strain curves that we generated. So the literature value we found was 40 MPa, which is right in the middle. Again, very happy about that. As Maggie talked about, we looked at an optical micrograph and found good evidence of crystallinity, and polypropylene is very able to be crystallized. I don't think crystallizable is a word, but yeah, so we're pretty happy about that. The delta H is actually pretty close. So we know that it's not as spot on as the other ones, but it's definitely in an acceptable window. They're also really happy about XRD. So we think that if you combine XRD, melting temperature, and ultimate tensile strength, it's very, very good evidence that it's polypropylene. So if you look, as Dylan talked about earlier, the peaks match up really nicely, and we think that's good enough evidence. This is the chemical structure of polypropylene, and we'll talk a little bit about its applications here later on. We decided that gamma was nylon 6,6. So if you look at the data that we found, the melting temperature that we got was 260 C, and the melting temperature for nylon 6,6 from literature is about 266. The crystallinity was not, we couldn't find crystallinity for, we didn't find evidence of crystallinity in our optical micrographs, but that's acceptable. Nylon 6,6, you can find crystallinity, but not always, so we don't think it's really detrimental that we didn't find it. If you look at the XRD plots, the PDF for nylon 10 alpha, I don't know what that is, but that's actually the only PDF that we have of nylon upstairs. So if you look at that, the peaks line up really well, so we think if we could find one for nylon 6,6, it would be pretty close too. We think XRD is really good data. We're also pretty happy about the delta H and the UTS. Again, they're not as spot on as the melting temperature or XRD, but we think there's ample evidence to suggest that it's nylon 6,6. References, can I answer any questions?